just gonna say about the competition. We have a post going up right about now in the King Contributors blog with more details about the submissions and what people actually wrote, and about the winners and about the runner-ups. So, very interesting stuff. Okay, we're going to talk about smart contracts. We're not going to code, but we are going to talk about what smart contracts are and what and how to code them. I'm going to talk about why they're so awesome, but why it's so complicated to create them. And we're going to try and draw some principles that apply to anybody who wants to be a developer of smart contracts. A little bit about me. My name is Oded Noam. I've been a software developer for a very long time, since about 1992. I've been doing this professionally from about 1994. Since 2016, more or less, I've been consulting businesses that are using blockchains as part of their operation. More recently, I've been holding two positions. I'm the head of blockchain research at Kin. Kin is the ecosystem for digital live services that Kik Interactive launched about 4 months ago. And it is today the most deployed, I think, mass market crypto wallet. And it is going to be a very significant force in the crypto world as we see it. I also hold the position of the chief architect of Orbs. Orbs is a company that develops a next generation blockchain platform aimed at mass market applications such as Kin. So I work at both positions. There's a very close collaboration between Kin and Orbs, that's both companies are doing really awesome stuff in blockchain. So if anybody here is interested in working in the best blockchain positions in the world today, they both happen to be here in Sarona. So we're looking for people both at Orbs and at Kin. So if anybody is looking for opportunities, you can raise your hand now, or you can come to us later. I'm sure you find the opportunities interesting. Okay, so let's start with talking about why smart contracts are so interesting. So let's begin with defining for those of you who are not familiar what smart contracts are. So the idea of using computer code as a type of contract dates back about 20 and something years. It was proposed initially by Nick Szabo in 1994. For those of you who don't know Nick Szabo, he's a very important cryptographer, and he's absolutely not Satoshi Nakamoto. You should know that. Now, in 1994, there wasn't a blockchain yet. Satoshi Nakamoto didn't exist then, of course. So, when Szabo designed smart contracts back then, he was thinking about smart contracts running on any regular computer. So, the idea is that instead of writing a contract in plain language or in legal plain language, and have lawyers or judges or the parties to the contract execute it, you can write the agreement in code and have the computer execute it. So if the contract refers to digital assets, then the actual execution of the code can actually move the assets, change hands, or whatever needs to be done according to the contract. So that's a very interesting property that smart contracts can enforce themselves. But that's not what's so great about it. Let's talk a little bit about the modern way smart contracts are used, and that's what we define as smart contracts of the blockchain. So for what we need, we can refer to a blockchain as a type of replicated state machine. That's technically correct, but what is a replicated state machine? A replicated state machine is basically in distributed systems. It's a system that each computer sees the same system state, and whenever we want to change that state, we just agree on the change and replicate the change between the different computers, so that every computer gets the state change, applies it, and gets to the new state. And that way, as long as the changes are always in consensus, everybody on the system sees the same state. And that's how distributed systems work everywhere. That's how distributed databases work, distributed file systems, and that's how blockchain works. So that's pretty typical when we're talking about a distributed ledger. We have the payments ledger. Somebody has a certain amount of money, that's system state. We get to a consensus about a transaction that transfers money from A to B. Once everybody's agreed on the contents of that transaction, then the new system state is where B has the money. So that's how Bitcoin works, for example. That's how all cryptocurrencies work. But with smart contracts, we can do something that's a bit more elaborate. We can run any code on a Turing complete machine, and that means any computer code, and we can get to a consensus over its outputs. So that's basically a smart contract. We can write our contract in computer code and use the decentralized system, it's called the blockchain, to agree on the outputs of our contract. Because that's in consensus, we can agree on the outputs of the contract. So that may not sound like much, but it is. Because what it provides us is completely decentralized backend for applications. And decentralized is really a huge concept. Why is it so? So I'll start with something that's completely unrelated. The internet. The internet is great. And I maintain that the reason the internet is great is because of decentralization. So we know that the internet is decentralized. Nobody controls it. Nobody can take it down. Nobody's in charge of it. Even though the people who initially developed the internet, the people who got it to where it is today, even though many of them are not around, it still keeps on evolving. The internet gets better and better, it keeps on changing, and it keeps being awesome and awesome. And it has kittens. So the internet is a type of DAO, a decentralized autonomous organization. So if we try to generalize why the internet is so great, the internet is an organization. There's ways that the internet operates. There's procedures of how it can do things. There's procedures of how the internet can modify itself, how it can adopt improvements or get better. And although it has all this, nobody controls it. There's no person or group of people that without them the internet would not exist or would not be able to improve. And it just works. It operates really well. It adopts changes, it improves, it evolves. That's all we expect from a successful organization. And decentralized organizations, they tend to be very robust. They tend to be more fair because nobody controls them, nobody can abuse them for their own good. They're very democratic, not always, but in many cases. And they have the potential of being disruptive in many industries, because many industries have some people in power who are at a risk of being corrupt and of abusing the organization for their own good. And decentralized organizations, they don't have that. They are more likely to act for the benefit of their entire user base or the entire universe, for that matter. So DAOs are really great. There's a small issue with DAOs is that it's a whole new form of organization. It's something that didn't exist. If you try to think about it, all the other types of organizations that we see are hundreds of years old. I mean, we have companies and we have foundations and we have nation states and we have churches, and they've all existed for at least 300-400 years, and some of them much more than that. But decentralized organizations, it's a new type of organ, and it doesn't fit a lot of the existing definitions. So, for example, a decentralized organization has no territory. It doesn't exist anywhere. It's not clear what legal framework it should apply to, and a lot of issues that the real world society has learned to cope with when it comes to dealing with companies or dealing with churches or dealing with nation states. These frameworks don't always exist when it comes to decentralized organizations. So let's agree that decentralized organizations are a good thing. What do we do if we want to create a decentralized organization? So the building block for decentralized organizations are decentralized apps. We can think of a lot of examples to decentralized apps. For example, email is a decentralized app. Nobody controls it. It just relays mails from server to server. The World Wide Web is such. They both operate over the internet, though email can also operate on other networks. So these are all decentralized applications. Now, if I want to develop new decentralized applications, I have a very difficult challenge to solve because I need to get enough people to use my protocol. I need to propose a protocol and get enough people to use it. And until I do that, that protocol would just not do anything. It would not be valuable to anybody. Because you have that critical mass that before you reach it, the network doesn't have any value. That's a big problem when we're trying to create decentralized apps. Sorry. So here comes smart contracts. Once we have a protocol for smart contracts and we have a blockchain that can execute smart contracts in a decentralized fashion, once we have that, and that blockchain has the critical mass that it needs to operate, now I can very simply, by deploying my code as smart contracts to that network, I can create a decentralized app. I mean, my app is installed on the blockchain and it operates. It has the critical mass it needs to operate, and it brings value to its users. So, in a way, it helped me circumvent the problem of reaching the critical mass. So here's an example of a trivial use case for a smart contract, because I've been talking about some big concepts, so let's go down to earth. A very simple smart contract of an escrow to exchange assets. So exchanging assets is something that requires a level of trust. And I met somebody on the internet, I told them, I want to sell you my CryptoKitties, bring me money. So we need to trust each other because somebody needs to go first and send their valuable asset, trusting that the other will send their asset. Now, the alternative is to use an escrow service. So we could go to a lawyer which we both trust, pay him something, and have him do the exchange. Or we could use a decentralized application, smart contracts, for doing that exchange. So I write the code for smart contracts that knows that it's supposed to get one CryptoKitty, one Ether, and then once both these conditions are met, the buyer would get the kitty and the seller would get the Ether. So that's very simple. And I know I promised there wouldn't be any code, but that's just to illustrate that it's not a lot of code. It's really a single contract and it does that simple task of exchanging assets. So it sounds very simple. We know how to write software, now we know how to write smart contracts. Awesome. Let's start creating decentralized applications. Now the problem is that writing smart contracts isn't exactly like writing software. So one thing that's very different between regular software and smart contracts is that smart contracts have a different use than software. We write software because we want to execute it and see its outputs. We write smart contracts because we want somebody else to agree with us on the contents of the code itself. So, in a way, when I'm going to write code, what I'm trying to do is convert the mental model that I have of what my software needs to do with a piece of code. But when I'm writing a smart contract, there's another process where I need to convert, translate my mental model to code, but that code needs to be translated to the mental model of the person reading the code. And that's the important part. I mean, executing the contract is secondary to having somebody agree to sign the contract. So that, of course, means that we need to write good code. It means that we need to write our code openly. We need to be open source, or at least share the code with whoever we're signing the contract with. And we need to provide tools that would help the reader understand what the code does. So I'll talk a little bit later about tests and about formal verifications, but it's important to give whatever tools people need to understand the code. The code by itself is not always enough. Another interesting property of smart contracts is that they need to be immutable. At least in today's smart contracts, the code itself needs to be immutable. And the reason is very clear. You wouldn't agree to sign a legal contract if you know that the document itself could change. Right? Because whoever wrote the contract could change it after your signature. You wouldn't write an empty page and let the lawyer draft the contract later. Or maybe you would, but it wouldn't be a smart thing to do. Now, if our code is immutable, if we need to write it once and for the code to be final, then we need to start with the final version of our code. But can we write the final version of our code to begin with? I mean, as software engineers, we have very bad reputation for being able to do things right the first time. When I was just starting out some 20-something years ago, somebody told me that every source file has at least one more bug, and that's always true. So just think how that applies to smart contracts. All smart contracts must have another bug. Another very problematic aspect of smart contracts compared to regular plain language contracts is that there's no code that can overrule them, or there's almost no code that can overrule them. So suppose, well, I'll tell you something. We know that software engineers write bugs, but you should know that lawyers also have bugs. And there's always an edge case that nobody thought of, and sometimes in life you get to that case and you find yourself in some weird situation where the contract just says something that you didn't intend when you signed the contract. So that also happens with real-world contracts. But in real-world contracts, if the results of the contract are absurd, then first of all, maybe the sides that signed the contracts could agree between themselves that the result is absurd and not execute the contract, and it's okay. Or if one of them wants to execute the absurd contract and another doesn't, then they can always try to appeal. They can go to a court of law and try to have the contract overruled. So that's possible. I mean, a judge could say that contract technically says something, but that doesn't make any sense, so we'll overrule the contract. And a court would actually try to estimate what was the intent of the people who signed the contract and try to make their ruling accordingly. And with computer code, that just doesn't happen. We have the interpreter, and whatever the code says, if the code has some weird, absurd bugs, then that's a contract. Now, of course, in extreme cases, when we have a bug in the code and that bug could cause damage of hundreds of millions of dollars, maybe we can have a consensus of the entire community that operates the smart contract that we should undo the results of running that contract. That's possible. It actually happened, for example, in Ethereum a few years ago, just about a year after Ethereum was launched. There was a very interesting proposition, actually the largest ICO to date back then. Today it wouldn't be considered that large. It was called the DAO, and the concept was very simple. It was a DAO that runs a venture fund. That's actually a very nice concept. It's a venture fund without managing partners. So anybody could send their money and invest in the fund, and the fund would choose its investments by getting to consensus with the stakeholders. Very interesting concept. It raises a lot of legal and ethical problems, and could be very interesting test case. Only that test case never got to be tested because there was a bug in the DAO code, and out of the $150 million that they raised, about 70 million were stolen. And because it was by far the largest activity in Ethereum at the time, the Ethereum community decided to change the Ethereum code and undo the transactions of the DAO. So technically that's very complicated, of course, because you need to figure out what to do with all the transactions and the following transactions that rely on them and everything. But that's also very controversial from the smart contracts point of view, because we had a contract. I mean, the thief, he didn't actually steal funds. He just abused the feature of the contract, which only he noticed. So is he a thief, or did he just use the contract as it was designed? That's a very big discussion. That's very controversial, of course. Actually, for those of you who don't know, the Ethereum network forked on that occasion. So today we have two Ethereums. We have Ethereum Classic, where the thieves of the DAO still have their money, and we have Ethereum where they don't. So there are two realities. Another big challenge with smart contracts is keeping them secure. So of course, I mean, we're among engineers. We know that we know how to write secure code, and everything's okay, and it's going to be okay. Trust me. But suppose your code is public. It's on the blockchain. Everybody can read it, and it holds millions or tens or hundreds of millions of dollars. Then even if your code is just as secure as you usually code, it makes you a huge target for attack. I mean, basically, if your contract holds millions, hundreds of millions of dollars, then people will try to hack it. And if there's any way they can steal your money, eventually they will. But it's not only about the target. So suppose my code is bug-free and you can hack the money out of it. But as the person who deployed the code, or as the person who controls it, I retained the permission to change the code or to make modifications to it. So somewhere in my home, in the back of the socks drawer, I have the private key that I can use to change that contract. Well, now I'm a huge target. And for hundreds of millions of dollars, people will be very assertive when they're trying to get that private key off of me. So they break into my house if that's required. They might kidnap my children, and they can do a lot of awful things. So part of being secure is not to retain any special rights, because that's really dangerous. And there's also the issue of liability. So, as many of you probably know, a main reason to use decentralized systems is that it disperses the liability in some way, in some magical way. Decentralized systems are not subject to a lot of regulation and don't have legal liability in many cases where centralized services do have. So, for example, if Amazon was down and my service was on Amazon, I could try to sue them for my damages. But if I was using a blockchain platform for my backend and it was down, I cannot sue the miners. They're not liable. So the lack of liability is a good reason that many people choose to use blockchain platforms. But notice that the platform is decentralized. That doesn't necessarily mean that your smart contract is decentralized. Because if your smart contract can be controlled with your private key, that means you're in control of that contract. So it's not decentralized, it is centrally controlled. So that could make you liable. So although there's no liability on the infrastructure, you need to make sure when you're writing the contract that you design it in such a way that doesn't create liability for you, unless you intend to. And again, don't give yourself special rights. So before we said don't give yourself special rights, if you
There's a microphone.
So we said don't give yourself special rights because you don't want to be hacked
or you don't want to be kidnapped, but you don't also want to appear in court or before Congress or any other situation where you're responsible for other people's money. So in a way, when you're a smart contracts engineer, you also need to be a security expert and a lawyer. Okay, so let's talk about a few principles for designing and engineering smart contracts. So the first, it may sound trivial, but it's something that software engineers are really reluctant to do, and that is to do their work well. That means you need to put attention to what you do. You need to design and get to the best design you can before you deploy your immutable contract. You need to write high quality code. You need to test it very well. You need to have unit test, integration tests. You need to check that you have proper coverage for your tests. There's the methodology of test-driven development, which covers all these issues, really recommended as a way of working, as the single way you should work when you're designing smart contracts. You should also use as much as possible sanity checks. When we're talking about sanity checks, that means that everywhere you can in your code, if you have an assumption in your head, that assumption should appear in code. And I'll give an example from Solidity development. Solidity is the language that's used for developing smart contracts on Ethereum. Solidity provides two types of sanity checks. It provides revert and assert, or require and assert. Require verifies that the input that your contract got is sane. So if you got insane input, you should revert, you should abort the transaction and not run the contract. And there's also assert. Assert means that the code is insane. So if there's a certain point in the code that shouldn't get, a certain condition that should never be met, or in a certain state it doesn't make any sense, then that should be an assertion, and that assertion should appear in your code. So sanity checks allow your code to test itself in a way. You should also make good use and very frequent use for code reviews and for professional audits. Now I mentioned formal verification. For those of you who are not familiar with the concept, when we're writing code, usually what our code does is whatever we want it to do. Now, with formal verifications, we're writing computer code that actually describes what our code does rather than how to do that. So it's not the algorithm for making the change, but rather defining what should be the relation of our inputs to the outputs. So that's a way to describe actually what we expect from the interfaces. So in many senses, the formal verifications are the contract part of the code. Only that the whole framework of formal verifications is in very initial stages. It's not developed yet to a sufficient state, so it's very hard to use formal verifications today. Not everything is covered in current technologies by formal verifications, and it's very complex to use them. Don't need to copy that. The slides would be on the slide share. but you can see the state of the development of formal verification tools for Ethereum on that link. I'd also want to comment that formal verifications are not a silver bullet. They don't solve anything. Like unit tests, formal verifications only test for what the developer thought of testing. So there's a lot of things that may not be covered by the formal verifications. I have a little example. I'm not going to explain exactly how it works or what it does, but just to show you how formal verifications look. This is a part of Ethereum code, and it uses formal verifications to verify that the function for binary search actually does binary search. So it proves that if the input is sorted as it's required by a binary search, then the result will be the correct result. Yeah. So the question is whether this code proves that it runs at the required complexity, and this code doesn't. Theoretically, it should be possible to write formal verifications that prove that. So I'm not saying that everybody should learn how to use formal verification tools and use them. I think it's recommended to a lot of people, but it's really hard in today's frameworks to do that. There are, though, a few features of the formal verifications framework that are already making their way into the Solidity compiler. So I'm going to give you one example. With the newer versions of the compiler can make proofs on whether assertions are reachable. So that's, I gave a very trivial and silly example, but here I have two assertions in my code. One would always be true, and that's okay. Assertions need to always be true, but another one could be false. So the second assertion asserts that 1 is equal to 2, and sometimes that's not true. So what we'd expect to happen with assertions is that this code, when I deploy it to the blockchain and I execute it, then the assertion would fail and an exception would be thrown, and I lose my gas and a lot of other stuff, but it would test the sanity of my program, and that's excellent. But the new features, which are the SMT checker that's available from the newer versions of Solidity, would also be able to prove that this condition could occur and prove this at compile time. So actually, this is what happens when I try to compile it. The compilation fails. So that's pretty awesome, because I discovered something that's a bug in my code, and I discovered it at compile time rather than at runtime. So that's very useful. And hopefully, pretty soon, the formal verifications, more features relating to formal verifications will make their way to this standard compiler. Another principle which is always true, but much more true with the smart contracts, is to make a real effort at keeping our code short and simple. Basically, whatever doesn't need to be part of the contract, part of the agreement, doesn't need to be on the blockchain, doesn't need to be a part of the smart contract. So a lot of times we have, the smart contract doesn't live by itself. We have our application, and our application has a front end, and it has its back end, and it has the smart contracts that it uses. So we use the smart contract only for the parts that need to be in consensus. But whatever doesn't need to be in consensus can remain in our back end or front end code. So one thing is to avoid the optimizations. Don't try to write super efficient code. You should optimize your code. You should write efficient code, you should compile with an optimizer, you should test your code with an optimizer. It's not trivial, not all bugs come up when you run the tests with unoptimized code. But you should also try to keep a lot of the code that you're using out of the blockchain. So if we are using off-chain logic, if we are using some of the logic in our web app, and only verify that the contents of the contracts are as they need to be on-chain, then we sometimes need to verify the correctness of what we did off-chain in the contract. So that's also a practice that you need to use. I'll give you a demonstration. You don't need to understand this code. I'm just going to show you something very simple. We have here two implementations of a function that calculates the square root of an integer. For some reason, I have a smart contract that needs to calculate the square root of a number. Now, the code that you see on the left-hand side does that. It calculates the square root. Believe me. But you shouldn't believe me, because it's not that simple. And it takes a leap of faith to know that the output of that code is actually a square root. Now, instead of that, I could use the code on the right, which also calculates the square root. So what that code does, it takes an extra parameter with a hint to what the result should be. That sounds silly. But all it needs to do now is to verify that the number that we got as a hint is in fact the square root of the number that we need to calculate the square root of. So that doesn't seem to make a lot of sense. But remember that this contract comes hand in hand with a back-end code that has math libraries and can very simply calculate square roots. So I don't need to implement my own version of square root. So actually using the silly square root makes a lot of sense in this case. Yeah. Yeah, so the question is whether it's like using lookup tables in embedded programming. So yeah, it's pretty much the same. And of course, if you're relying on lookup tables in your code, then unless the lookup tables are hard coded into the contract, if they're stored in the platform storage, then you need to verify that the whatever stored there is correct. Another interesting property of smart contracts that you need to be aware of is that there are no secrets on blockchain. If you have a random seed, if you have some code that you don't want people to know in advance what it's going to result, then you have a problem. Because anybody can see your code. Anybody can see the contents of your memory. Anybody can simulate the outputs of your code, and everybody can debug them and see what happens inside the machine. Well, there's a lot of code for a lecture that wasn't supposed to have code. But what I have here, and I'm really not expecting you to read the contents. The font is too small even for me to read. But that's a famous example. A few months after Ethereum was released, somebody posted on Reddit, here's a contract for playing tic-tac, not tic-tac-toe, that's for playing, rock, paper, scissors on blockchain on money. How cool is that? Well, it is cool. You can bet somebody that you're gonna win, and they vote for whatever they're gonna pay, and then it's your turn, and then you can check the blockchain and see what they played. So no secrets of blockchain. Last but certainly not least is to write secure code. So there needs to be a methodology for writing secure code. First of all, you need to do a risk assessment. Try to understand how are people going to attack your code. What parts of the code should be better protected. You should audit your code. Internally and externally, you should use good auditing services. We've been, my company, we've been involved in many ICOs in the past year. We've been using very expensive and very professional services that audit code with security audits. You should work with several, you should get recommendations on what auditing services are good, which ones are useful, because they're not all good. You should also make sure that you're updated with the industry on security risks. Sometimes new risks are discovered. Not always everybody are aware of whatever attacks are possible. You should be in touch with your community. You should continue reviewing your code as long as it's live. You should continue auditing it and making sure it's secure. If you find out that some new exploit is applicable to your code, make sure your users know that. Be transparent about it. Rather that they hear it from you than that they hear it once they want to install it. Also, if your code is high profile, if it's an ICO or something and you're getting a lot of traffic, have bug bounties. I mean, a lot of people think that with open source software, whatever bugs you have, people are going to discover them. Well, I tell you something, people are not going to look for bugs in your code unless you pay them. So a bug bounty program is a good way to do that. If somebody finds a security problem in your code, they should be paid for it. And another thing is you can also open your code for some sorts of maintenance. So you can have updatable contracts. Of course, that's a problem. That both creates a liability and it's a risk to the immutability of your code. But you can have parts of the code upgradable. You can use upgradability in several ways. Of course, you should use it cautiously so that you don't create any liability and you don't risk anybody's money. I'm going to make it. It's okay. It's okay, I'm going to make it. Another technique which is a lot of times more useful than updatable code is just to have a circuit breaker. So just enable your code to disable so that if there's a known security hazard in your code, you're not able to change your code because that would create a big risk or a liability. But you'd be able to disable your code so that everybody can get their money back and switch to a new, safer version. So implement a circuit breaker. A lot of times I recommend using time locks or transaction throttling in combination with circuit breakers so that if there's a bug found, then whoever's stealing money won't be able to steal all of it by the time you've touched the circuit breaker. And keep monitoring your code. If there's monitors you can use off-chain that will monitor the state of the contract, the amount of money in it, see if anybody's stealing money off of it so that you can detect that right away, do that. have an operation center, have an incident response team in place. That's it. For those of you who want to read some more, here's a few links with some good reading on that subject. Of course, it's all very, the whole industry in a very preliminary state, so it's a practice that still develops. Any contributions would also be welcome. So, thank you. Any questions? Slides are going to be on slideshow. Yep. Okay? Yep.
Hi, I have a question about smart contracts. And you said that everyone can see the contents of the smart contract once it's updated. Since you control like the composition of the contract, can't you like upload a contract where you encrypt the contents and only people with the right keys can read what's inside? You just have it stored on the blockchain?
You can do that. Oh, well, you know, encrypted code is a big challenge because basically you can, well, the interpreter needs to be able to interpret the code. So if the interpreter knows what to do with the code, then a person could theoretically do that. But you can obfuscate the code. You can make it harder to read, harder to debug. People are doing that. That's basic anti-cracking that people use in regular software, where they don't want the code to be reverse engineered. That is possible. You can also use cryptographic techniques where the code doesn't actually run on the blockchain, but rather runs on personal computers. But you have blockchain code that verifies the execution of off-chain code. So that way you don't open your code at all, but you just have proven outputs of code run off-chain, and this smart contract on-chain can verify them.
Yeah. So, two questions. One, in the square root example you had, I was wondering why the compiler, why a recent version of Sol 3 would even compile it, since you used assert rather than require when you in the right side. So can you get back to the slide for a second? Thank you. Yeah, that one. So you see, you used assert rather than require, and since this assertion can fail, wouldn't the compiler? Shouldn't the compiler block even compiling this contract? That's supposed to be the difference between require and assert, right?
Well, the difference between require and assert is not that the errors necessarily become compile time errors. The SMT checker can make them runtime errors. The logical difference between assert and require is that assert points to a bug in the code and require points to a bug in the input. And I chose to use assert in this case because there is a bug in the code, probably in the backend code. And assert is just about being less nice to an attacker so that they lose their gas.
Yes.
But you could say that require would be just as good in this case.
Okay, and another question, unrelated to this, but during the Keen ICO, when you switched from Ethereum to Stellar, where it's no longer Turing complete, did it cause any problems with the previous code you had, and how did you overcome the issues of non-Turing complete code in Stellar?
Well, that's an interesting question in general. So what happened in Keen is that we had smart contracts during the ICO, and we plan to have more smart contracts later this year when we launch the Keen rewards engine. But at the moment, Keen is only used as a currency. So at the moment, there are no smart contracts that are in place. The ICO already ended and the KRE was not yet launched. So in the meantime, we have a window in which we can use Stellar, which has sufficient scaling capacity to our needs, and it's good enough for now. When we need smart contracts later, we need to find a solution that's probably not Stellar.
So basically, you use Stellar just for tokens, and then you are going to change these tokens back to tokens in an ERC20 when you need to do something more sophisticated.
Not necessarily ERC20. That depends on whether Ethereum would be good enough for our needs by the time we need that. ERC20 is proven very problematic for an application like Keen. Today's transaction costs, for example, they're just unreasonable for transactions like the ones that we have in Keen. And for another example, when we launched one of the first use cases in the Kik app was in December. And for those of you who remember, nobody could do anything on Ethereum in December. So that's a very big problem for an app that has real users that have something they want to do on the blockchain. So Ethereum is very problematic, and we might be looking for another platform that supports smart contracts when we need it.
Thank you.
Any more questions? Okay, thank you.
Thank you.
So we're going to host another event in a bit more than a month. Leonid is going to host the next event. You want to host another event? Oh, okay, another question. So let me just finish with introducing the next event. Leonid is going to teach you how to lose millions of dollars in your Ethereum smart contract. It's been done and it can be done again. So if you want to learn how, please come. Yeah, another question.
In web dev, we usually do a hello world and a to-do list. If somebody's trying to get into programming Solidity, what would be the first couple of the projects? Chessmaster, what should you build?
You can start with a hello world, although it doesn't make sense as a contract, but it doesn't make sense as a program either. So it's okay.
It's like the to-do list of Solidity.
That's well. I hear a lot of ideas here. I said let's open it for discussion in our Reddit or something. Yeah, let's do an ICO for ideas to a Hello World project in Solidity.
What's that?
Yeah, well, actually, that's a good idea. Crypto assets as a means of gaming are going to be the big thing, because we know it was a big hit in December, so now everybody in the world is trying to be the only one who's going to launch one in February. So just, I don't know, crypto ferrets or crypto doggies or something like that. Anything else?